Welcome, everyone. This is part 4 in our series on natural language inference. We're going to be talking about different modeling strategies. And you might think of this screencast as a companion to the associated notebook that explores a lot of different modeling ideas and suggests some architectural variations that you might explore yourself. I thought we would start by just considering hand-built feature functions because they can still be quite powerful for the NLI problem. So some standard hand-built feature ideas include, as a kind of baseline, word overlap between the premise and hypothesis. This is giving you a kind of pretty small feature space, essentially measuring how the premise and hypothesis are alike. If you want to step it up a level, you could consider the word cross-product features, which would just consider as its feature space every pairing of a word in the premise and a word in the hypothesis. This will give you a massive feature space, very large, very sparse. But the intuition behind it might be that you're allowing your model a chance to discover points of alignment and disalignment between the premise and the hypothesis. And so that could be very powerful. You might also consider additional word net relations, bringing those in. These would be things like entailment and contradiction, antonymy, synonymy. And those, of course, could be nicely keyed into the underlying logic of the NLI problem. Edit distance is another common feature. Just a raw float value between premise and hypothesis as a kind of high-level way of comparing those two texts. Word differences might be a nice juxtaposition with word overlap. You could be considering ways in which the premise and hypothesis contrast with each other in that feature space. And we can also move to alignment-based features. I mentioned that word cross-product is kind of an attempt to have the model learn points of alignment between the premise and hypothesis. But of course, we could also do some things kind of even before we begin to learn feature weights, trying to figure out which pieces in the premise correspond to which pieces in the hypothesis. We could consider negation. We've seen, of course, that that's an important indicator function in a lot of NLI data sets. There's a powerful intuition behind that, especially as it pertains to contradiction. And so maybe we would write some feature functions that were explicitly keyed into the presence or absence of negation in various spots in the premise and hypothesis. And we could also step that up a level as well and consider more generally all kinds of different interesting quantifier relationships that would hold possibly at the level of an alignment, as in item 6 here, between the premise and hypothesis. And this is kind of keying into the underlying logic of the NLI problem. And then finally, named entity recognition. We've seen that these features might be important in figuring out which entities co-refer across the premise and hypothesis. And so having some devices for figuring that out could be useful as a kind of low-level grounding for your system. Now let's move into a mode that's more like the deep learning mode, because as we saw earlier in the screencast series, these models have proven at this point to be the most powerful models for the NLI problem. And so it's productive to think also about different deep learning architectures. And I'd like to start with what I've called here sentence encoding models. And the most basic form of that would return to an idea of distributed representations as features. So the idea here is that we have in this diagram the premise and the hypothesis. So the premise is every dog danced, and the hypothesis is every poodle moved. And our approach using distributed representations, the simplest one, would be that we're going to simply look up all of those words in some fixed embedding space, which would be like a glove embedding space, for example. And then we're going to separately encode the premise and hypothesis by, for example, doing the sum or average of the vectors in each of those two texts. And so that gives us a vector xp and xh. And then we might concatenate those two or do some other kind of comparison like difference or max or mean to get a single fixed dimensional representation x that is then the input to a kind of, could be a simple softmax classifier. So all we've done here is take our old approach using distributed representations as features and move it into the NLI problem where we have both a premise and hypothesis. And I've called this a sentence encoding model because we are separately encoding the two sentences. And then the model is going to learn, we hope, something about how those two representations interact. On this slide and the next, I've given a complete recipe for doing exactly what I just described. I'm not going to linger over it here because it's also in the notebooks, and it just shows you how using our course code, it can be relatively easy to set up models like this. Most of the code is devoted to doing the low-level processing of the words into their embedding space. Here's the rationale for sentence encoding models. I think this is kind of interesting, right? We might want to encode the premise and hypothesis separately in order to give the model a chance to find rich abstract relationships between them. The sentence encoding approach might also facilitate transfer to other kinds of tasks, right? To the extent that we are separately encoding the two sentences, we might have sentence level representations that are useful even for problems that don't fit into the specific NLI mode of having a single premise and a single hypothesis for the sake of classification. And that could be an important part of that vision from Dagan et al. That NLI is a kind of source of effective pre-training for more general problems. Let's move to a more complex model. We'll follow the same narrative that we've used before. We just had that simple fixed model that was going to combine the premise and hypothesis via some fixed function like sum or average or max. Here we're going to have functions that learn about how those interactions should happen, but we're going to follow the sentence encoding mode. So I have our same example, every dog danced and every poodle moved. And the idea is that each one of those is processed by its own separate recurrent neural network. And I've indicated in green that although these two models would have the same structure, these are different parameters for the premise and hypothesis. So they function separately. And then in the simplest approach, we would take the final hidden representation from each of those and combine them somehow, probably via concatenation. And that would be the input to the final classifier layer or layers that actually learn the NLI problem. So it's a sentence encoding approach in the sense that H3 and HD are taken to be kind of separate summary representations of the premise and hypothesis respectively. And we have a vision that those representations might be independently useful even outside of the NLI context. Now, in the associated notebook, NLI2 models, there are a bunch of different implementations, including a full PyTorch implementation using our PyTorch base classes of the sentence encoding RNN approach that I just described to you. And I thought I would just briefly give you a high-level overview of how that modeling approach works, because there are actually just a few moving pieces and the rest is kind of low-level implementation details. So the first thing that you need to do is modify the dataset class so that conceptually it is going to create lists of pairs of examples with their lengths and their associated labels. By default, the underlying code that we're using expects one sequence of tokens, one length, and one label. And here we just need to raise that up so that we have two, as you can see here. Every dog danced, every poodle moved. Both happen to have length 3, and their label is entailment. So we make some changes to the dataset class to accommodate that change in format, essentially. Then the core model for this is conceptually just two RNNs. And the forward method is just essentially bringing those two pieces together and feeding them to the subsequent classifier layers. And so that's very conceptually natural, and it's just down to having two separate RNNs that you implement using the raw materials that are already there in the code. And then finally, for the actual interface, the Torch RNN sentence encoder classifier, this is basically unchanged, with the one modification that you need to change the predict proba method, the fundamental method for prediction, because it too needs to deal with this different data set format that we established up here. And that is, again, a kind of low-level change. And so what I hope you're seeing is that the first and third steps are kind of managing the data, and the middle step is the one that actually modifies the computation graph. But that step is very intuitive because we're basically just reflecting in code our idea that we have separate RNNs for the premise and hypothesis. And then finally, I just want to mention that a common approach you see, especially in the early literature, is a sentence encoding tree NN that has exactly the same intuition behind it as the RNNs that we just looked at, except that the premise and hypothesis are processed by tree-structured recursive neural networks. And since the underlying data sets often have full parsed representations, this is an avenue that you could explore. It can be tricky to implement these efficiently, but conceptually, it's a kind of very natural thing where you just repeatedly have a dense layer at every one of the constituent nodes on up to a final representation here, PB and PD, that is then fed into the classifier layer in just the way we've done for the previous models. So those are the sentence encoding RNNs. Now let's move to a different vision. And I've called these chained models because they're going to just mush together the premise and hypothesis as opposed to separately encoding the two. Of course, the simplest thing we could do in the chain mode would be to essentially ignore the fact that we have two texts, the premise and hypothesis, and just feed them in as one long sequence into a standard recurrent neural network. And since that involves no changes to any of the code we've been using for RNN classifiers, it seems like a pretty natural baseline. And so that's depicted here. And actually, this can be surprisingly effective, right? The rationale for doing this, in this context here, you could say that the premise is simply establishing context for processing the hypothesis. And that seems like a very natural notion of conditioning on one text as you process the second one. And correspondingly, at the level of human language processing, this might actually correspond to something that we do as we read through a premise hypothesis text and figure out what the relationship is. And here's a simple recipe for doing this. The one change from the diagram that you might think about is that I did, when representing the examples here, flatten them out, of course, but also insert this boundary marker that would at least give the model a chance to learn that there was a separation happening, some kind of transition between the premise and hypothesis. But that's just the level of featurization. And in terms of modeling, you hardly need to make any changes in order to run this kind of experiment. We could also think about a modification that would bring together sentence encoding with chained. And this would be where we have two sets of RNN parameters, one for the premise and one for the hypothesis, but we nonetheless chain them together instead of separately encoding them. So as before, I have a premise RNN in green. I have a hypothesis RNN in purple. They have the same structure, but different learned parameters. And the handoff is essentially that the initial hidden state for the hypothesis is the final output state for the premise. And in that way, you get a seamless transition between these two models. And this would allow the model some space to learn that premise tokens and premise sequences have a different status than those that appear in the hypothesis. And let me just close by mentioning a few other strategies, because this was by no means exhaustive, but it's kind of interesting at the high level of architecture, thinking about sentence encoding versus these chained models. So first, the torch RNN classifier feeds its hidden state directly to the classifier layer, but we have options like bidirectional equals true, which would use as the summary representation both the final and the initial hidden states essentially, and feed those into the classifier. So it's a different notion of sentence encoding or of sequence encoding. And other ideas here, right? So we could, instead of restricting just to one or a few of the final states, do some kind of pooling with max or mean across all of the output states. And different pooling options can be combined with different versions of these models, either sentence encoding or chained. We could also, of course, have additional hidden layers between the classifier layer and the embedding. I've shown you just one for the sake of simplicity, but deeper might be better, especially for the very large NLI data sets that we have. And finally, an important source of innovation in this and many other spaces is the idea of adding attention mechanisms to these models. And that's such an important idea that I'm going to save it for the next screencast in this series.